Hello, I welcome you all in this presentation related with the subject fundamentals of the manufacturing processes, and we are talking about the methods used for improving the properties of the bulk materials, mainly the surface properties. So in the previous presentation I have talked about the methods which are used for improving the surface properties without modifying the chemical composition, and in this presentations the processes wherein the chemical composition of the surface is modified in order to improve the properties of the surfaces. So there are various mechanisms which are used to modify the composition of the material according to this for this purpose, means like this is the component whose surface properties are to be improved. So near surface layers of the component are composition of the near surface layers is modified by having the suitable environment. Like say normally certain alloying elements which will be helping to improve the properties of the surfaces, mostly like in the ferrous systems, like introducing the carbon or nitrogen or boron or vanadium, etc. All these help in improving the formation of their phases and compounds at the surface layers. So the properties, especially hardness, wear resistance, sometimes residual stresses are also favorable residual stresses are produced, which help in improving the properties of the components being made by the manufacturing processes. So the basic approach is to modify the near surface layer microstructure, wherein basically change in composition helps in bringing the suitable formation of the suitable phases, compounds, intermetallic compounds, carbides, borides, martensite, etc. So basically the compositional modification is done to have the suitable type of the constituents near the surface or near surface layers, so that the suitable type of the properties can be developed. And for this purpose, some common elements which are introduced in the surface of the ferrous metals mostly are in form of, like say, carburizing. Carbon is introduced in the carburizing process, nitrogen is introduced in the nitriding process, boronizing process introduces the boron, vanadizing introduces the vanadium. So in these processes, so this is one category of the processes where some kind of the diffusion is involved for modifying the near surface layers, and this is one category of the process where diffusion is the mechanism which helps in modifying the near surface layer composition. There is another set of the processes wherein we put at the surface, we put the suitable material, like it is called pre-placing. Put the suitable material at the surface, and then this material is melted with the substrate material using suitable heat source. So heat source is used may be used in form of like laser beam, plasma, or TIG arc. So accordingly we say that the laser alloying, plasma alloying, or the TIG alloying. So here material is placed and it is melted with the using suitable kind of the heat source, so that it forms the integral part of the substrate and near surface layers composition is modified. So this approach is basically the melting. So melting is another approach where in the surface layer composition is modified through the use of these sources of heat, maybe electron beam or laser or plasma, or the flame also can be used for this purpose. There is another set of the process where near surface layer composition is modified through the use of the ions. So high velocity ions are directed onto the surface. So what we do basically in this case, the metal vapors are allowed to move up, so they get deposited at the surface of the component whose properties need to be modified, and then ion beam is directed onto the surface. So a high velocity ions when directed onto the surface, when they impact due to the high kinetic energy, near surface layers is affected by the two ways. One, crystal structure is deformed and damaged, and the second one, whatever the metal vapors are getting deposited, like in form of nitrogen or some other kind of the elements whatever we want to introduce. So these atoms will be getting deposited onto the surface of the component or surface of the substrate, and when the ions impinge on the surface of the component to be modified, it deforms the crystal structure as well as mixes these ions and atoms with the substrate. So near surface layers composition is also modified and the crystal structure is also damaged, and a combination of these two will be leading to the modification of the crystal structure as well as the surface layer composition through the use of the ions. So these are the three approaches: melting, use of the ion beam, and the diffusion, where the crystal structure as the surface layer composition is modified so that suitable combination of the properties can be realized. So if we see here this slide, it shows the kind of elements that we need to introduce. So the kind of elements that we need to introduce will depend upon the purpose for which we want to modify the surface composition and the design of the component. Purpose means what is the extent of the improvement in hardness, what is the depth of hardened layer is needed. Like in some of the cases, the depth of the hardened layer, this may be means depth of the modified zone or surface hardened layer, this may be just 1 or less than 1 micron in like ion beam modified methods, the methods wherein ion beam is used. While in other cases the depth which is modified, say in case of the laser cladding, laser alloying or TIG alloying, this depth may be even 1 mm or so, while in other cases where nitrogen and carbon are introduced at the surface in carburizing and nitriding methods. So this depth may be like say from 100 micron to the 1000 micrometer or even more. So depending upon the depth, depending upon the hardness properties needed at the surface and the depth of the hardened zone, these parameters will be governing the process that we need to select for the modification. Apart from these functional requirements, the component design of the component which is to be modified also affects, because we need to accommodate that into the process so that the modification can be facilitated. And if the design is too complex, then heating and cooling, differential heating and cooling can lead to the distortion and the dimensional modification, so that can be a problem. So under those cases, when the geometry is complex, the component is bulky, so we need to use such processes where differential heating and cooling is minimum, and for that purpose, like the plasma assisted carburizing and nitriding are found useful, because the rise in temperature of the component is limited as compared to the conventional carburizing and nitriding processes. Now we will see the details a little bit more, like say if the steel hardness is somewhere say 600 to 800 HK noob hardness, while the hardness of the other zones is this is say 1800 to 2000 HK hardness. So this is the hardness scale. So if we see the low carbon steels, they will be having the hardness very low hardness. This is for low carbon steels, and when their properties are modified suitably using like say carburizing, nitriding, then the properties get improved, then the hardness gets improved, and we get a much wider much greater hardness. And as compared to this one, so this may be like say carburizing, this may be for nitriding, and so here it is about the processes being used. And on the other hand, we have the boronizing kind of the process, which much higher hardness is realized. So this is what we can see in this diagram, wherein as per the hardness levels, the low hardness for the simple steels, but low carbon steels will be having further lower hardnesses, and when they are carburized and the nitriding is performed, there is increase in hardness takes place, like say from the 800 to 1000 HK. Boronizing causes further significant increase in the hardness, say which may be in the range of like say 1600 to 1000 HK. So, depending upon the kind of process, the different hardness values can be realized, and accordingly we need to select the suitable kind of the process. So, the functionality or the property requirement as well as the design of the component affects the selection of the suitable kind of process. Now, we will see the general approach in all these processes which are used, whether it is carburizing or nitriding or boronizing. In all these processes, what we do, like the substrate component is taken like this, and then suitable rich environment is created all around the component, and these atoms in the very nascent state at high temperature, when high temperature, under the high temperature conditions, when environment rich in either carbon or nitrogen or the boron is created around the component. So, because of the compositional difference, they starts getting diffused. So, there will always be compositional gradient, maximum will be at the surface and it will be decreasing as we go down below the surface. So, accordingly the depth of the hardness, means the extent of improvement in hardness will be changing. So, this is what has been shown in this diagram, wherein the requisite element rich environment, either in form of plasma, ions or metal vapors, in atomic state or in ionized state or plasma state, is created all around the component to be modified. So, suitably say like chromium or nitrogen, carbon, boron or silicon rich environments are created. These will be getting diffused into the substrate, and once they are present, they will be improving the properties as per their action, whether they will be forming borides or nitrides or the carbides, or it may be leading to the formation of the martensite. So, as per the kind of elements which is being added, it will be forming different types of the compounds and the phases which will be having the different characteristics. So, accordingly there will be different kind of improvement in properties of the component up to the different level. Carburizing is one of the most common process which is used, and as name appears, in carburizing, carbon rich environment is created all around the component for introducing the carbon near the surface of the component. So, which type of the components are carburized, that is what is to be seen, like the components wherein we want that core is tough while surface is hard. So, this kind of the properties are offered by the low carbon steels. Low carbon steels, as we see this diagram, carbon content low carbon, so it will be offering you higher toughness, and the with the increase of the carbon content, so there is a reduction in the toughness value. So, if the properties are like this, so at while in terms of the hardness, there is continuous improvement in the hardness. So, when the carbon is low, say 0.1, the toughness is high but the hardness is very low. When the carbon is high, the hardness is high but the toughness is very low. So, what combination we want, that surfaces are hard corresponding to the 0.8 level of the carbon content, while the core remains still tough. So, for this purpose only, the core composition is maintained while the surface composition is enriched with the carbon. So, for this purpose only, the carbon is introduced near the surface layers, and this can be introduced up to the depth of say 0.1 to 1.5 mm, depending upon the purpose for which it is to be introduced. So, once the carbon gets enriched near the surface layers, and this enrichment is done up to the point like say 0.8 to the 0.6 to the 0.8 weight percentage. Once the carbon is enriched at the surface, so this will be leading to the higher carbon content in the steel, high carbon steel, but high carbon steel which is simply enriched through the diffusion process will not be increasing the hardness, because it will be leading to the formation of the iron carbide. Actually what we need, that whatever carbon has been introduced in the steel, that is transformed into the martensite, and that is why what we do, the kind of thermal cycle which is used for the carburizing purpose, increase in temperature up to the range of say 850 to 950 degrees centigrade, and it is held for the time as per the requirement of the depth to be modified, where in depth modified or depth carburized is found proportional to the square root of the time. So longer is the depth, greater will be the longer is the time for carburizing, greater will be the depth which will be enriched with the carbon, and then it will be cooled. So after cooling in, again it is heated to the austenitic state, so that it forms the austenite. For the carbon content, since this is the this will be leading at 0.8%, it will be leading to the eutectoid composition of the steel, wherein upper eutectic temperature is 730 degrees centigrade. So heating up to say 800 degrees centigrade will be leading to the formation of the gamma, that is austenite. So once the homogeneous austenite is formed, it will be quenching it hard. So quenching will be leading to the formation of the martensite. So basically objective is the first heating and holding is done for carburizing purpose, and once this is over, carbon enrichment has taken place. Thereafter again it is heated, so that homogeneous austenitic state is achieved, and followed by the rapid cooling or the quenching, so that hard martensite is formed. This is the kind of heat treatment cycle which is used for the purpose of the carburizing. We know that the carburizing is a diffusion based mechanism, wherein the diffusion is found a function of the temperature as well as time. So higher is the temperature, greater will be the rate of diffusion, greater will be the depth up to which carbon will be introduced in the modified surface or carburized surface. Similarly, greater is the carburizing time, greater will be the depth up to which carbon will be enriched. So depth of the carburized layer will be the function of the time and temperature both. So this is what we can see here as per the another diagram, wherein what we can see, if the carburizing time we mention here in the axis scale, and the depth of the carburizing is seen in the y scale carburizing, then there will be continuous increase in the depth of the carburizing with the increase of the time, and the rate of increase is faster for the like say if it is 850 degrees centigrade, the rate of increase in the depth of carburizing is slow as compared to the case when depth of carburizing is high. So at 950 degrees centigrade, this is what we can see here in this diagram. What it is showing is schematically that near surface layers will be having the higher carbon content as compared to those which are below, and the depth up to which carbon is able to get diffused into the substrate, that is called carburized layer. And the depth of the carburized layer we can see here increasing from as a function of carburizing time, it is increasing. At 850 degrees centigrade increase is limited, while at 950 degrees centigrade with the as a function of carburizing time, increase in depth of the carburizing layer or carburizing depth is increasing at much higher rate, and this is attributed to the higher rate of the diffusion of the carbon into the iron at the higher temperature. And we know that since the carbon directly affects the kind of phases which will be formed, the kind of the amount of the hardness, amount of the martensite which will be formed, and the hardness of the martensite. So both the carbon increase in carbon content increases the martensite fraction and the increases the hardness of the martensite both. We know from this diagram that the martensite may be found, but the hardness is less, like this, maybe like say 30 or 40 HRC, and with the increase of the carbon content this may be like say 60 to 65 HRC. So what we can see here with the carbon content 0.2 and with the carbon content 0.8, so even if the martensite is formed, it is a very low carbon. At if the carbon content is very low in the martensite, hardness will be low, but the hardness increases with the increase of the carbon content. and it becomes maximum say around 60-65. So, carbon directly affects the amount of the carbon present at the surface, directly affects the fraction of the martensite which will be formed, as well as the hardness that will be obtained. And as we go down below the surface, what we can see here, there is a continuous drop in the hardness because of the decreasing carbon content in the subsurface region. This is the typical method. There are three ways of the carburizing. One is the solid carburizing, this is also known as pack carburizing, then liquid carburizing and gas carburizing. So, in all these cases the concept is same, where carbon rich environment is created around the component so that it can get diffused into the surface. And here in the pack carburizing or solid carburizing, the steel chamber filled in with the charcoal and a limited amount of the oxygen leads to the formation of the carbon monoxide, which decomposes into the carbon and oxygen, and that leads to the introduction of the enrichment of the carbon into the component being modified. So, this is what we can see, and this is a typical heat treatment cycles which is used for the carburizing purpose. Initially the heating, then holding, during which carbon enrichment will be taking place, then step cooling is carried out for avoiding the unnecessary the residual stress formation, or we can say the distortion tendency due to the thermal shock kind of conditions. So, step cooling helps in avoiding the cracking as well as the distortion tendency. Thereafter, rapid quenching helps to have the martensite transformation, and after the martensite is formed, it is tempered. So, this many times in the solid carburizing, direct quenching is not practically workable. So, what is done? First the pack carburizing is done in the box, then components are taken, then again it is reheated for heat treatment purpose, and thereafter it is quenched. While in case of the liquid carburizing, it is somewhat easier because we can take out the sample easily from the bath, and then we can quench directly into the water or any other suitable medium for quenching purpose. So, liquid carburizing can help directly in heating in one go, then followed by quenching to achieve the desired hardness, while in case of the solid carburizing, we need to do the heating twice, first for the carburizing purpose and second for the hardening purpose. Another mechanism is the or the surface modification approach is the nitriding. Carburizing we know is done in the austenitic state, so heating is done above the upper critical temperature so that homogeneous austenite can be formed, and a lot of carbon can be introduced in the austenite, which is having the FCC structure and can accommodate lot of carbon and has the higher solubility to the carbon. While in case of the nitriding, the approach is different. Nitriding is always carried out in the ferritic state. So, normally the heating is done up to the temperature of 500 to 550 degree centigrade, and in the of course in the nitrogen rich environment. So, in a box basically ammonia is heated. So, ammonia breaks into the nitrogen and the hydrogen, and this nitrogen gets diffused into the surface of the component at the high temperature in the ferritic state, of course. So, 500 to 550 degree centigrade is the normal thing which is used. So, in this process basically the nitrogen will be getting introduced at the surface in the ferritic state. So, basically it will be leading to the formation of Fe3N or Fe4. Fe4N. So, these are the kind of compounds which are formed at the surface, will be having the more nitrogen concentration as compared to the below surface regions. So, a typical white layer is formed at the surface where higher concentration of the nitrogen exists in, and this white layer becomes very hard, very brittle, and so it has lot of cracking tendency, and therefore normally this white layer after the nitriding is removed, so that we are left with the only the stable nitrides at the surface, which can offer the improved properties in the material. Simple for the nitriding for the simple steels is not that effective because it will be leading to the simple formation of the iron nitride only. So in order to have the more effective nitriding process, certain steels having the presence of vanadium, chromium, aluminum, these are added so that they can form their nitrides effectively, and that is why certain alloy steels are found more suitable for nitriding purpose, and these alloy steels generally have the concentration of good concentration of the vanadium and chromium, because their nitrides are very hard and stable. So they will be leading to the more improved and effective nitriding process, and the resulting properties will also be better. So this is the general principle of the nitriding process. This is what we can see here, and effectiveness of the nitriding is also different for the different alloys because of this difference. So we can see as a function of the nitriding time, since the nitriding is also diffusion based processes, so when the nitrogen rich environment is created with the help of ammonia, it will be leading to the diffusion of the nitrogen into the steel surface. So if we keep on increasing the nitriding time, the depth, the amount and the depth up to which nitrogen will be introduced at the surface, that will be increasing. So what we can see here, there is increasing hardness, increasing depth of the nitride layer, which will be produced for minimum hardness of like say 50 HRC. So this is the condition that for minimum increase in the hardness of the 50 HRC, the depth up to which this much improvement in the hardness is achieved is like say this depth is increasing at lower rate for this is steel 4340, while the rate of the improvement is much faster for 4140, and it is much faster for the nitro alloy. So the reason for this is attributed to the presence of the different elements in the different amounts, which will be having more affinity to the nitrogen, and they will be forming more hard and stable nitrides. So this is what we can see in the typical nitride surface. We will be having a higher concentration of the nitrogen. So eta kind of the nitride is formed at the surface, then gamma nitride is formed below that, and then diffuse nitrogen is present below that. So since because of the difference in the nitrogen concentration, maximum at the surface nitrogen concentration, and then below that it is somewhat lesser, but this is the zone where then nitrides will be formed, that is the compound formation will be taking place, while further below the nitrogen concentration is lower and nitrogen is there in the diffused state in the steel. So these are the zones which will be subjected to the greater hardness levels due to the nitride formation. Plasma nitriding and the plasma assisted carburizing, these are another set of the processes where instead of the decomposition of the gases into the atomic state, here directly these constituents like active nitrogen and carbon are obtained directly through the plasma formation, and when the plasma is formed for using the suitable kind of the gases, so that we have desired carbon and nitrogen in the environment, and this is achieved using quite low temperature like 300 to the 800 degree centigrade and under the pressure of 300 to 1000 Pa. And when this kind of the nitriding is carried out, when the nitriding is carried out in the plasma state of the carbon and nitrogen, it can the process is much faster, it takes lesser time, and the maximum temperature generated to the component is also lower. So one then modified zone near the surface layer is formed after the modification. The laser alloying is another method where the surface composition is made through the surface composition is modified through the alloying purpose, and the general approach for this is the basically pre-placement method, and the component or the constituents that we want to add is identified as per the requirement of the purpose, like say carbon is steel. If we take an example of the carbon is steel, if its composition, if its corrosion resistance is to be improved, then we will be putting a layer of the chromium over it. So because chromium is known to improve the corrosion resistance, and then chromium is melted using the beam of the laser. So basically laser beam is directed onto the pre-placed chromium, and then when laser beam directed, it melts the chromium as well as it melts little bit the surface of the base metal. So this is how the kind of the mixing of the element placed at the surface and the, is taking place with the substrate. So the dilution levels in this case are much higher, maybe we'll say 25 to 50%, where lot of melting of the base metal takes place for mixing of the elements being placed at the surface. So this is how the composition of the surface layers can be modified in order to achieve the desired properties at the surface. So this is what we can see here in the laser alloying. This is the substrate, and the element to be introduced is applied in form of the paste over the substrate, and then laser beam is passed. So wherever there is a laser beam, there will be the molten state mixing and mixing of the substrate material with the material placed over the substrate, and after the solidification will be leading. After the solidification, we will be getting the modified zone. So this is how we introduced the elements at the surface, and that is how that's why it is called laser alloying. So if we see this component which has been laser alloyed, what we can see here, the thin, this is the substrate, and near the surface layers are modified using the nickel and phosphorus coating, and this modified zone is extremely small, maybe like say 5 to 10 micrometer, and this is realized like by before pre-placing, before we pre-place the material to be alloyed, and then laser beam is passed over the surface, so that the mixing of the material pre-placed with the base material after the melting leads to the formation of the alloyed layer. This is another example of the laser alloying, where the material placed at the surface properly mixed with the base metal and forms the very coherent modified surface layer, which is very solid. This is the ion implantation method, as I have explained. This is the substrate material and atomic arrangement in the substrate material, and the material to be incorporated at the surface is evaporated, and these metal vapors will be getting deposited over the surface, and when the ion beam is directed at high velocity onto the surface, so this will be leading to the increased mixing of the these atoms with the substrate material, and thus the surface layers get modified, and in this process the surface layer crystal structure is also modified. So we will see that the most of the ions and the metal vapor atoms, all these are present at the surface, and their concentration will keep on reducing with the increase of the depth from the surface. So here now I will summarize this presentation. In this presentation, basically I have talked about few approaches like carburizing, nitriding, ion implantation. Basically it is the nitrogen ion implantation which is used very commonly for improving the properties, and then laser alloying. These are the methods which can be used to modify the surface layer composition for improved properties of the components. Thank you for your attention.